We have already studied circular motion. In that motion, we have an object following a circular trajectory, so its trajectory is not a straight line. It does not follow a uniform motion. By Newton's first law, this means that the object experiences an acceleration. This acceleration, which we call centripetal acceleration, is always pointing to the center of curvature, that is, the center of the circumference. This happens even in the case where the speed is kept constant. The speed does not change, but the velocity does, as its direction changes. If there is an acceleration, there has to be a force inducing it, because the force is proportional to the acceleration and it points in the same direction. This force has also to point to the center of the circle. We call this force the centripetal force. For example, in the case of a satellite orbiting the Earth, the only force experienced by the satellite is the gravitational force of the planet, of the Earth. This force happens to keep the trajectory circular and is pointing to the center of the orbit. In this case, the gravitational force is the centripetal force. In the case of a car turning, the centripetal force is the force of friction that points to the center of the curve. For the mathematical expression for the centripetal acceleration, we found where v is the velocity of the moving object and r is the radius of the circumference. If we substitute this into Newton's second law, we obtain for the centripetal force that F sub c is equal to mv squared divided by r equals to m omega squared times r. From this equation, we see a direct relationship among the centripetal force, the radius of curvature, and the velocity of the moving particle. Every object that has a circular trajectory will be described by that expression, where F sub c is the centripetal force that will depend on the particular physical system under study. Let's look at a specific example. Let's think of the moon revolving around the Earth. We will assume that the trajectory is circular, which kind of is. The centripetal force on the moon is equal to the mass of the moon multiplied by its velocity squared and divided by its radius of curvature. Because the velocity is the distance traveled in a time t, for a circular trajectory we have that the distance traveled is 2 pi r. So we end up having that the centripetal force is equal to the mass of the moon times 4 times pi squared times the distance r divided by the period squared. We know that light needs 1 second and a quarter to go from the Earth to the moon.
Preparing to fire laser at the moon.
Make it so.
There it is. There's the spike.
2.5 seconds for the light to return. That's the moon. We hit the moon.
That's your big experiment? All that for a line on the screen?
Yeah, but think about what this represents. The fact that we can do this is the only way of definitively proving that there are man-made objects on the moon, put there by a member of a species that only 60 years before had just invented the airplane.
Because light travels at 300,000 kilometers per second, that means that the distance of Earth-Moon is about 380,000 kilometers. To know the velocity of the moon around the Earth, we can use the fact that a full moon repeats every 28 days. 28 days times 24 hours per day times 3,600 seconds per hour gives us 2,419,000 seconds as the period of the orbit of the moon. That leaves us with the centripetal force equals to the mass of the moon times 4 times pi squared times 3.8 times 10 to the power of 8 divided by 5.85 times 10 to the power of 12. The mass of the moon is 7.35 times 10 to the power of 22. The centripetal force of the moon caused by the Earth is then 1.5 times 10 to the power of 10 newtons. Let's see another example. Let us think of a car turning at a banked curve. The reason why some curves are banked is to make it easier and safer to take curves in motorways. In these cases, what the inclination of the road is doing is making part of the normal force be included in the centripetal force. The forces we have here are the weight of the car, the normal force, not vertical anymore, and the friction between the tires and the asphalt. If we decompose into vertical and horizontal axes, we have that for the vertical there is the weight pointing downwards and the normal force pointing times the cosine of alpha pointing up. In the horizontal axis we have the friction pointing to the center of the curve and the normal force times the sine of alpha also pointing to the center of the curve. In the vertical axis there is no acceleration, so it is equals to 0. In the horizontal axis we have the centripetal acceleration, so this is equal to m times v squared divided by r.